So I said scientists wanted to classify their reagents, okay, and they needed a classification. So, and they came up with three. So all the substances we use in the laboratory are either acids, bases, or salts. And I said, these two, these two, how do you draw that? They react together to give this third guy. Acid and bases react together to give salt. So for that reason, I'm mostly going to be talking about acid and bases the most, but then I'll now teach you about salts, how to form salts, and all of those things. Now watch. You see, the definition of acids has evolved over time. So the first one, there are three scientists that define acids. The third guy, is like evolution, okay? So you study something, you notice an attribute, you describe it, then others study it, they notice another attribute, they advance your definition. Are you getting it? So that's basically what's happening here. So the first guy, in 1887, Svante Arrhenius. We've discussed this, okay? But she wasn't around. So, Svante Arrhenius. Thank you.
I did not share.
Oh. No, I'll send it to the group. So, Svante Arrhenius was the first to define an acid. And he basically defined the acid based on his principle of ionization of substances. His principle of what?
Ionization of substances.
Alright, and that principle states that when substances dissolve in water, ionization means that dissolution in water to split up. First, ionization only happens to substances that are polar. Substances that are what? Polar. I don't want to say ionic bond alone, because you soon notice that, or you soon know that, for example, we've talked about it, water is not electrovalent bond, right? It's held by covalent forces. But then it's polar, yeah? So substances that are ionized are substances that are polar, but all electrovalent bond or ionic bond compounds are polar. So when substances are ionized, they dissociate into freely moving charged particles called ions, right? And there are two types of those ions. We have the cations and the anions. That's just reiterating what we discussed. So he now based his definition of an acid on that ionization. He said an acid is a substance which, when dissolved in water, will produce hydrogen ion or hydronium ion or hydroxonium ion. Hydroxonium ion. Okay? Some sources might say oxonium ion, but it's basically these two, hydronium or hydroxonium. Now they refer to the same thing. Look, it is still this guy. Now what he is saying is that when this guy dissolves in water, when substance like HCl dissolves in water, it will become H plus and Cl minus. So it is a substance that dissolves in water to produce hydrogen ion as the only positive ion when dissolved in water. Notice? So when it dissolves in water, it produces hydrogen ion as a positive ion. Every other ion there will be negative. Make sense? Because the reason why I'm saying this is because when we get to salt, you see acidic salt. So it is not an acid, it is an acidic salt, meaning that it has proton too, and it has hydrogen ion, but it is not the only positive ion. Had it been the only positive ion, that substance will not be a salt, but an acid. Alright. So now see H2SO4. If it dissolves in water, it will produce H plus SO4 2 minus. To balance it, we have two hydrogens, we put 2 here, and one H2SO4, and one SO4. So this is balanced. But here's the point. This is the only positive ion. But then where do we come up with hydrozonium ion? He is saying that this thing will dissolve in water. Here, we intentionally are not showing the water there. Let's show the water. When HCl actually dissolves in water, what happens is it will it will donate this hydrogen ion to this guy. So it will form H. What will happen is we have H plus H2O. Exactly. So this is what forms H3O plus. So this is what we call hydroxonium ion or hydronium ion. Exactly. Then plus the later part which is negative. So that is his own ideology of an acid. But then in a later year, in about I think 19 early 19 this 19th century, 1887. So early 20th century, two scientists came up with the idea of another kind of reaction that they saw with this thing, acids, and it makes sense. Okay, but before we talk about those ones, he now defined a base as a substance which when dissolved in water will produce hydroxide ion. You remember a base is a metallic oxide. That's the physical nature of a base. Exactly. That's what you see. The chemical formula now. A base, for example, Na2O, CaO. These are bases, metallic oxides, bases. But as they are like this, when they dissolve in water, they become what is called alkali. But remember that it is not all bases that can dissolve in water. Okay? I will give you a mnemonic for things that are soluble in water and things that are not soluble. Because they've asked in Jambo that which of these salts is soluble. It's basically with salts. Now, generally, all OH minus are any substance that have OH minus, they are not soluble, except if it is Na that is bonded to it, that is in NaOH or KOH. Is it clear? And ammonia too, ammonium rather, ammonium ion. So it is only that time that those things will be soluble. Once it's not this, for example, if I give you MgOH2, will it be soluble? Do you understand now? So except this guy, everything, every compound formed with Na and potassium, they are soluble. Because when we were creating them in heaven that day, I remember they put sodium. That sodium, in fact, from what I recall, that day that we were making it, I think I was one that said they should, that since it's soluble, so we should call it makes sense. Alright, let's go. That was just a joke. Now, like I said, he defined acid as one that will produce hydronium ion as hydrogen positive ion, but a base as the substance which when dissolved in water will produce hydroxide ion. Is that correct? Hydroxide ion was always negative, so that was his own concept of acid and base. So we call it Arrhenius acid and Arrhenius base. Arrhenius acid, Arrhenius base. So in about 1819 something, I can't remember the year too, but that Lewis season is 1923, from what I remember. So the second definition now came on board about the description of what an acid and a base is. Is that clear? Do you have this note? Do you snap it? So that I clean the board. Oh, okay. So now in that early 19th century and 20th century, we said the two scientists came again to define acids and bases. I already told you how to remember this guy, Bronsted and Lowry. I've forgotten their full name. Brown. So they now define acids as now when, for example, in that thing that formula we wrote, H2SO4, when it dissociates becomes H plus and SO4 2 minus. Now, what are you seeing here? Now, you see this H plus is also called, what I say H plus is also called? Proton. Thank you. H plus is also called proton. So, because whenever this guy dissolves in water, it produces this guy, then it means that it can always give this guy to anything it is reacting with, right? So because of that, they define acids as proton donors, as a proton donor. Acids are substances that donate a proton to another thing they react with. Then they now define a base as proton what? Acceptor. God bless you. Proton acceptor. Is it making sense? All right. So, for example, if I react and okay, no, there was something I wanted to now show you. The concept of conjugacy. Okay. Now watch it. So he said if I ionize that guy, it gives me H plus also for 2 minus. Now this guy is the acid. But when it comes here, it forms, this guy becomes the conjugate acid. And this is called what? Conjugate base. Thank you. This guy is called the conjugate acid. This guy is called the conjugate. On this side of the reaction, let's show because it's reversible. So, on this side of the reaction, what conjugate acid and conjugate base simply means is that this guy is able to give, the acid is what that protonates, right? So this guy is able to give this guy its proton and it becomes this back. So because it's the giver, we call him the conjugate acid. This one the acceptor, the conjugate base. Now, look at this one. If now if we now dissolve H2SO4 in water, what will it form? H3O plus what? SO4 2 minus. They will balance out. Okay. Balance it yourself, okay? But here's the point. We have H2SO4 and H2O to give this guy. Now, who in this reaction, watch out, this guy. Now, let me first show you the dissolution of water itself. You know when water is water, it ionizes, right? To give what? H plus and OH minus. So water itself forms what? A conjugate acid and a conjugate good. Because the conjugate acid is one that is donating the proton, right? And this is the one that is accepting the proton. Now you soon see something about acids. You soon see something about water. That's why I needed to show you that. Here, water is reacting like an acid, right? It's giving someone proton. So here, let's see what's happening here. Now this is an acid. Now let's see if this acted as a base. See what he did. Now this guy gave this guy acid, right? So this guy became acidified. Do you understand that? So, yes. So this will be conjugate acid, right? And this guy conjugate base. Let me just put CB. Now, so here for what I'll put CAC. Now, this guy here is our actual acid. This one have what? Base. So you saw water behave like an acid here. We are seeing it behave like base here. Let me show you again another thing. Another reaction. Let's say reaction between, let's use ammonia. Ammonia, when ammonia reacts with what dissolves in water, this is what it forms. We have Na NH4 plus OH minus. What do you notice here? Now, this guy has been acidified, right? Or protonated. So we call it what? Conjugate acid. This is what? Now, if this guy is the conjugate, watch, there's something I want you to notice. This guy is the conjugate acid. And here, the guy it came from is the base. So the guy that became conjugate base came from the acid. So here, this guy that became the conjugate acid here will be the base. Is it making sense? Then this guy that became the conjugate base comes from the acid. Is it clear? So here's what I want you to see. You saw water acting as what here? Water acting as what here? So that property is called amphiproticity or amphoteric. We say water is amphoteric, that's the short one. Or amphiprotic. Amphiprotic. Amphi. The word amphi means both sides. Amphibians, do you remember? Alright. Or amphoteric. So water is amphoteric or what? Amphiprotic. I think I prefer what did you say? No. I think I prefer amphiprotic. Do you know why? Because amphoteric, we reserve, but they mean the same thing though. Amphoteric simply means substance that can behave both as an acid and a base. Amphiprotic kind of say that it can donate proton or accept proton. See, it accepted a proton here, right? Acting like a base. See, it donated a proton here, acting like an acid. Is it clear? If you are confused, don't lie, raise your hand. God bless you. Now let's go to the third definition of an acid. Okay. Now the third definition came in, I think, 1923 by Gilbert Lewin. So that guy was my friend too. We sat beside each other in primary school. He liked rice. You saw that? Oh. If I was lying, she would have said it. Do you understand? Is it if I was lying or if I were lying? If I were. Exactly. If I were. Now we said G.N. Lewin. Gilbert N. Lewin. I've forgotten the N. Lewis. G.N. Lewis. Do you know why I said Lewin? The designer of one of my shirts. T.M. Lewin. So I misplaced it. G.N. Lewis, okay? So, now in 1923, he defined acid as an electron pair. Now what? It's the opposite of what Brunelleschi said. What did Brunelleschi say acid is? Proton donor. What's the opposite of proton? Electron. So what's the opposite of donor? So it's what? Electron pair acceptor. Is it making sense? And a base will be what then? God bless you. Don't forget to electron pair donor. Lewis acid. Electron pair acceptor, Lewis base, electron pair donor. Let's see if it's observable here or if it is noticed here. So for example, this guy is an acid. Let's see water first. H2O. H plus OH minus. Now, using Lewis diagram you needed to know Lewis structure first, right? So let's see what happens here. What does this H plus mean? This H plus mean here means this guy has how many electrons? How many electrons are in H plus? Zero. There is no electron here. What does positive charge mean? What does positive charge mean? If you see positive charge in an ion, what does it mean? See,
Giving out
yes, it gave an electron, right? That's the meaning of positive charge. So that this guy is positive and it's plus one. So what does that mean? It gave out, it's only one electron. Do you understand? But this guy here, let's see what this guy did. In the Lewis structure of this guy, we'll have one, two. This one of the distinct will bond here, right? So we have 1, 2, 3, 4, 5, 6. Now, what does? Are you going on?
no.
Okay. Is everything alright? So what is happening here is this. This water is acidic here. Do you know why? It is acidic here because it is accepting an electron pair from this guy. No. It is accepting, yes, an electron pair. That's why when it dissociates here, it becomes negative here. Let me show you in this reaction. Yes, it is reversible. Once it's ionization, it's reversible. Exactly. Have we done chemical kinetics? No. Okay. We'll do it. Okay. Now, what did we say? We said that this guy is the base, this guy is the acid. So what does an acid do? An acid accepts an electron pair. So now, let's see if an acid, who is the acid here? Water, right? Okay, now, let's see if it accepted an electron pair. When this guy got here, which one shows acceptance, collecting of electron? Is he this place or this place? This side, right? So you saw that what is showing is that this guy accepted a pair of electrons from this guy. So because this guy gave an electron, is this guy more like gave this guy an electron, so became this. Is that correct? So this is the base electron pair donor because it's the one giving here. So here we are seeing that it gave, that's why it's possibly charged. Then here is showing that this guy accepted the electron. Conjugate base. Is it clear? One of the reasons why Lewis acid is it's not like it's the most acceptable. All the three explanations are acceptable. It's a broader view of what an acid is. So it means that for substances to behave like an acid, they don't need to have hydrogen again. Yes, they don't need to have hydrogen again. That's what gives rise to, you know, I said bases are metallic oxides. Okay, so what does that mean? It means an acid with what? Non-metallic oxide. So that's why we call them acid anhydrides. We call them what?
Acid and
Anhydride. The word an means not. That is, water has been removed. Is everything all right here? TML. Is everything all right? No? Should we talk about it later? How can she tell you? That's good. Calm down, okay? Don't worry, God is here. Nothing can happen to you. Even if lion come here now, one time I kill it straight down. God bless you. You see, if I was going to say it now, you think, Master, just now. So what did I say? Make sure you are listening, okay? Right. All right. Now, so let's talk about salts now. I've told you about how we form salts, right? You simply react an acid with a base to give what? Salt and water. Now that reaction is called neutralization reaction. The reaction is called what? Neutralization reaction. Now how does an acid and a base become a salt? Now first, the definition of salt is that a salt is a substance that is produced, a salt is a substance that is produced when some or all the replaceable hydrogen ions in an acid has been replaced by a metal or ammonium ion. The salt is a substance that is formed when some or all the replaceable hydrogen ion in an acid has been replaced by a metal or ammonium. Now, you could also see it as a salt is a substance that is formed when the replaceable hydrogen ion has been completely replaced or partially replaced by a metal or ammonium. Now let's see such reaction. That reaction is called the neutralization reaction. Why do we call it neutralization? Because the base neutralizes the acid. Now, give me a base, metallic oxide, KOH. Okay, that's metallic hydroxide is an alkali. Don't forget to, a base is an alkali is a soluble base, right? Alkali equal to soluble base. Keep in mind also, we just discussed about ammonia being a base. There was a jam question that was asked one time, which of these is a base? And ammonia was there. So ammonia is a base. All right. Three. Yes. Ammonium is NH4 plus. Don't misplace it though. NH4 plus. It reacts like a metal. Of course, plus. Make sense? Now let me react this guy with an acid. Let me use HCl. I like to use simple things first. So when they react, it's very easy. Watch me. You will take this guy and this guy because they are the ones that will form water, right? So this is H2O. So I come here and write H2O, then KCl. Keep in mind that I told you that in the electrovalence bond, we always write the metal before the, or generally we write positive before negative. All right. So KCl. So we have KCl. So this is the salt and this is water. You see the way I formed it, yeah? If I reacted this guy with K2O, I'll still get KCl plus H2O. But this is just a special form of this. Why? Because this is basically this that is added to water. Is it making sense? I have dissolved this guy in water. So, is it correct? Now let's talk about phases quickly so that you understand how to put phases. You see, there are, I think, 4 phases. The first phase is liquid. The second one is solid. The third one is gaseous. The fourth is aqueous. With liquid, if the phase is liquid, you put L, you put sub L, solid sub S, gas sub G, aqueous sub AQ. Let me show you how to know it. It's very simple.
I don't feel like it's
Why do you know?
You are right with because I don't very good at
I say, must have been feeling it of himself. Let me show you how to identify it. So there are substances that generally come in liquid form, never solid. Exactly. Example, H2SO4. H2SO4 is generally in liquid form. So if I want to react H2SO4 with something, for example, H2SO4 will be, now wait, the H2SO4 we use will be liquid, exactly. But I cannot react that liquid H2SO4 directly. I have to dissolve it in water. Is that okay? It's called dilution. It's called what? I'm trying to dilute it. So, makes sense? So, the diluent we use is what? Water, right? So, by diluting it, it becomes aqueous. Aqueous simply means soluble in water. Aqueous simply means what? Can dissolve in water. So, if that thing is not soluble in water, it will form what is called a precipitate. We'll do this thing. Separation technique. We'll do it, don't worry. Precipitate. So when it precipitates out, it will crystallize, it will turn to solid back. So when something is not soluble, you put S. Do you understand now? Don't worry. I'll give you a trick to know insoluble salt and insoluble salt. You will see that once you write a salt, a chemical reaction, neutralization chemical reaction by itself, you can know the phases. Exactly. Now, like I said again, I'm going to reiterate. I said that liquid is things that generally come in liquid form. Exactly. So, for example, I know, give me something that comes in liquid. Yeah, H2SO4, like we said. But H2SO4, if it's reacting, you will not put liquid. Do you know why? You don't use the liquid directly. You have to first dilute it in water because it's too concentrated. Do you understand? So you have to dilute it to aqueous. Then gaseous form is gas. For example, HCl. Watch. We'll fix. I want you to see something. HCl. They will call it. There are two ways to call it. There are two ways to pronounce acid. If you mention the hydrogen, for example, you say hydrogen tetraoxosulfate 6. You won't put acid. Should I reiterate? You want to call acids, okay? Let's say I write an acid on the board like H2SO4. Instead you call it hydrogen tetraoxosulfate 6. Or call it hydrogen sulfuric acid. Or tetraoxosulfate 6 acid. Is it clear? So without the hydrogen, you add acid. With the hydrogen, you don't add. So this is called hydrogen chloride. And in that phase, this one is even with respect to phase. When it's gas, we call it hydrogen chloride gas. Is that okay? The one we use in the laboratory, of course, is liquefied. So that one is hydrochloric acid. Is it clear? Alright, so that's about phases. So here now, let's fix our phases. What would this be? Gas, right? What would this be? Now, this one is easy to know because it is gas. This one what? Aqueous. Because we know that it has been dissolved in compression. Now here, what are we going to have here? Now wait, I told you any substance that has K or Na in it will be what? Soluble. So what would this guy be? Aqueous, God bless you. Then this guy is always liquid. Well, not always, because there are sometimes we have steam. Alright. But for your neutralization reaction, it's always liquid. Water is always liquid. Now, this phase, of course, will be aqueous because you see dissolving this guy. If this guy is supplied as gas, well, I don't know. Let's supply it as aqueous. Do you know why? If you supply it as gas, if this guy is solid, K potassium oxide, I think I've seen, no, what I've seen is quicklime, the powdered form. I think this one too may exist in the powdered form. Okay? But generally, if you want to react a salt like this too, we'll wet it, we dissolve it in water. So I'm guessing this should be aqueous or so, for which reason this is soluble and it will dissolve in water. Is that clear? So this is also the water. Is that clear? Alright. Come write the forward reaction for this reaction I want to write. Balance the reaction and give me their phases. Yes. No. Give me their phases also. This is lead. I've told you how to interchange ions. Okay, I'm going to do it now though. So for your face, it's the only thing that is wrong. Gracious for gracious for. So your reaction is balanced. Just change the face. That is PB. PB. Yes. Exactly.
Okay, because this is so, this is advanced.
This is so. Yes. Watch. Watch. The substance that these two things will produce is salt and water. So you don't know how to identify an acid. Well, at least for a starter, you can easily just say any guy that you see H plus there is acid. Okay? That you see H, then another radical acid. But a salt will be a metal and a radical. Any radical apart from OH. Exactly. So when this guy reacts, and most of you got the forward reaction, but not the face. This guy, this is the component that will give us water, right? So I bring it here, H2O. So the remaining components to combine, PbSO4. I was surprised you even got it because I was thinking you put two somewhere. I know she's sharp.
She grabs things with what
And that, if you see the shape of her nose and my nose, you see that. What?
just needs consistency.
Yeah, and to be reading every day. Alright, let's go. So I said that PB is 2, right? So an SO4 is also 2. So 2 cancels 2. That's why we are living like this. Now to balance out, I think from what I saw, you put 2 here, right? So now the phases. This guy will be supplied as aqueous. You usually supply acids as aqueous because except for HCl, I don't know. But you usually supply acids at what? Aqueous because you have to dissolve the. Now, do you add acid to water or water to acid? Now you add water to acid. Acid to water, water to acid. Water to acid. Exactly. All right. Of course, we know that's the is a precaution in the laboratory, right? The point is this that this guy is supplied aqueous, but this guy all OH, all substances have OH minus, apart from this guy and Na, they are what insoluble. So for that reason, this guy was what solid. Is it clear? Now the salt that this led to forms. Hmm? Now the sulfates are generally soluble. Sulfates, they are generally what? Except a few that I will mention. Exactly. A few. I think I have like two mnemonics or three mnemonics. So the one that suits you is the one you use. Exactly. So this sulfate is actually insoluble. The sulfate of lead is actually insoluble. So the what? So exactly. And this one is what? Liquid. Right. Is it correct? Now, I'm going to clean this. Now, let's quickly talk about the strength of an acid and the basicity of an acid. Because now, generally, if you are asked which ones are strong acids, okay, now, strength of an acid. Now, the strength of an acid is basically the measure of how ionizable, the measure of ionizability of the acid. So, acid that ionize, so we have strong acids and weak acids. Strong acids ionize completely. They undergo what? Complete ionization. But weak acids, they undergo what? Partial ionization. Now, strong acids generally, they are HCl, H2SO4, and HNO3. These three guys are what? Strong acids. Then weak acids are H2CO3, H3PO4, H what again? 2SO3. Is it clear? These guys they ionize partially. Ammonia will be a base. It's not an acid now. Is this clear? Because this concept will help us to understand the next thing I want to talk about. It's called basicity of an acid. Then we'll now talk about types of salts that are formed. Now the basicity, we said that salt is formed when the replaceable hydrogen ion in an acid has been replaced by metal or ammonium rather. But remember that, since I said replaceable, it means there are some hydrogen that might not be replaceable in an acid. Is that clear? So, so the basicity of an acid is the number of replaceable hydrogen ion. Is that clear? The basicity of an acid is the number of replaceable hydrogen ion in an acid. So, for example, HCl. How many hydrogen ions are replaceable here? One. This one, what will be the basicity of this one? Two. What will be the basicity of this one? What will be the basicity of this guy? Basicity of this guy? Basicity of this guy? Good. Now, other weak acids that we mentioned. Do you remember ethanoic acid? Ethanoic, all those oiks, right? What's the basicity of this guy? God bless you, basicity of this guy. The basicity of oic acids are usually one, especially when we get to organic chemistry. I'll teach you they are higher carboxylic acids. So this one is a simple carboxylic acid. We call them monocarboxylic acid. Exactly. Mono because it has only one COH. There are some that have up to two COHs. We call that dicarboxylic acid. Exactly. Dicarboxylic acid. So my point is now is that so for a dicarboxylic acid, what will be the basicity? God bless you. It means that there are two COHs there. Exactly. Then should I give you an example?
That's H2O.
No,
Sorry, H2O.
no, I said carboxylic acids now.
Okay.
Look at this guy. Now, you will notice that I put COH at the end. They are terminal functional groups. They never stay in the middle. Exactly. How many bonds are between oxygen? Two. What will be the hybridization of this carbon?
S S SP SP2. Is that speed? Ah,
What's the hybridization of this carbon?
of
This carbon.
SP5.
Of this one, let's number from here. Carbon 1, carbon 2, carbon 3. What's the hybridization of carbon 1?
SP. S.
Don't follow your neighbor. You what's the hybridization?
SP1.
You? SP2. You? SP2.
Yes.
You? But you changed you were saying SP. You? SP1. That's SP, right? Yes. Rahima. When you know here we did hybridization, covalent bond though. So this guy is SP2. Once you find one double bond around the carbon, SP2. Is it clear? Eh? What will be the hybridization of this one? The carbon 2. S SP3.
Five. 1, 2, 3, 4 now. SP.
1, 2, 3, 4. SP, that's 1S, 1P, 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 that's 3 Ps, that's 4. 4 things, 1, 2, 3, 4. Exactly. The way to know it is very simple. We have SP, SP2, SP3, SP3D, SP2D. Alright, this is the highest. Okay? Now watch. SP means 1S and 1P. So it means when two things are around something, then that thing what? SP hybridized. Is it clear? When three things are around an atom, then that atom what? SP2 hybridized. So look here. This guy has 1, 2, 3 things around it. So it will be SP2. Make sense? Is it clear though? Alright, so this one is SP3 because it has 1, 2, 3, 4.
Okay, the answer that you
No, they ask you just one. You don't, what do you mean for the whole? No one. What? Finish your food. You know when your love was eating yesterday too, she started to see visions. Oh, I wanted to show you what's the basicity of this guy. The basicity of what? 2. It should be 2. Why? Because there are 2. When this guy ionizes, let me ionize this guy. This in Nigeria is called propane dioic acid. Exactly. Now, this one is ethanoic. When this guy ionizes, it becomes CH3, CO minus plus H plus. So notice it's donating only one hydrogen. Exactly. But here, this guy is donating, he's going to donate this first hydrogen and this second hydrogen. So we'll call it, we say the basicity is what? 2. Alright. That's what we need to know about basicity. Now let's talk about types of salts quickly. Now what are the types of salt? The first one is a normal salt. The first one is what? The second one is a salt that has acid, that has acidic property. So acidic salt. The second one is what? Basic salt, yes. And the third one, fourth one is a double salt. And the fifth one is a complex salt. Now, normal salt is when there is equal supply of acid and base. So not one is more than the other. But acidic salt is formed when there is less supply of acid and less supply of the base, then more supply of acid. E.g., H2SO4 reacting with KOH, for example. OH is supplied one here, right? The basic portion is supplied as just one. It's just one OH we have, right? To give here. Now, it means if you keep supplying KOH in excess, if you keep supplying it, it will neutralize back to normal salt. But in the initial stage, it will form KHSO4 plus H2. Now, why will this form? This will form because there is excess supply of the proton, but less supply of base. Is it making sense? But normal salt, there is equal supply. Now, there is another thing you have to know. If I now react this, for them to be equal supply, for example, H2SO4 should react with something like MgOH2, equal supply, such that we have MgSO4 plus H2. Is it clear? But if I now react H3PO4 plus Na2O, for example, the amount of base that is supplied is still less. So do you understand now? So that is what makes a salt acidic. So this one is still a salt, but it's what? An acidic salt. Same goes for sodium hydroxide. I've told you this is called caustic potash, right? Caustic soda also, if you react it, initially you get NaHSO4. How do we name this? Potassium hydrogen tetraoxosulfate 6. Potassium hydrogen tetraoxosulfate. Potassium hydrogen tetraoxosulfate. You haven't inquired, you said so, yeah? Thank God. That was just a joke. Alright, now watch. How do you think we'll form a base then? A basic salt then? When there's excess supply of of what now? Base than acid. Exactly. Can you give me an example of such reaction? Maybe HNO3, let's use NO3.
And then ammonia.
Ammonium, yes, but okay, ammonia is the base, yes. And no, there's no excess supply of the base in ammonia. It doesn't show excess supply. Let me show you the one that shows excess supply of base. That one I used MgSO4, MgO2 rather, or CaOH. There's one hydrogen supplied here. There are two being supplied here. Is that clear? Are you getting it? So since there's excess supply of this guy becomes CaOH, then NO3. Now, is this balanced? CaOH, NO3. I mean, plus what I get that, but I was talking about when they react. No, no, I'm not talking about the balancing. Leave you balance it yourself. Is that clear? So, but you will notice here that this guy still has OH. The OH has not completely left, right? So because of that, it is a basic salt. Excess supply of base, that's just how to know it. Acidic salt, excess supply of acid, basic salt, excess supply of base. Now listen. Then when do we form acidic salt and basic? Okay, the name. This will be um, calcium tri, how do you name MgOH SO4, for example. This will be magnesium hydroxy tetraoxo. So calcium hydroxy trioxonitrate. Is that clear? Hydroxy. Now, double salt. We talked about double salt, alum. Double salt is just salt that contain more than one salt. Is that clear? Example is alum, right? Do you remember this guy? Alum that we use in water. See, it contains two salts, right? So, but it's also hydrated. It's an hydrated salt. So that's the last thing we'll talk about. Hydrated salt. So then complex salt is this. A salt that is formed by a complex. That's the meaning. That if you draw the structure is in a complex. Alright. Example is only one I think I remember. That is Fe bonding with Fe bonding with I think is it cyanate or ammonia? I think it does it with cyanate. CN6. Ever seen this before? Cyanate. So Fe ENH 3 6 plus. Alright? So the way it does it is this. The full structure, you tell me the shape it will form. The full structure will look like this. F1 to NH like this. 1, 2, 3, 4, 5. Is it complete now? F is, I'm sorry. So this becomes NH3 around, NH3, NH3, NH3. Plus 1. Now, so you can see, now what will be the shape? Now you can see that it forms a complex. Exactly. That's what we call a complex salt. Now, what's the distance? The shape, the geometric. How many things? What will be the hybridization of that ion? What will be the hybridization of this ion?
Okay,
The SP is, the maximum is 3. D2, God bless you. 6 things are combined. S, P, D. 1, 2, 3, 4, 5, 6. So one bond there is forming the S orbital, another bond there is forming the P orbital, another bond there P, another bond there P, another bond there D. Is it clear? Alright, so that's the average SP3D2. The shape, octahedral. Octahedral. Can you not see that? This one is going into the board, out of the board, up and down. Is it clear?
yeah, that you showed us that people that they are all 90 degrees.
Yes, give me 5. Bond angle. Bond angle 90 degrees. Alright, so are we done with this? Alright, hydrated salt. Copy it quickly. Hydrated salts. No, will you quickly snap it so that we can make it? It's a video so that I can just. Let's go to hydrated.
Your face. Yes,
Now we go on. Will you? She'll send it to the group. Exactly. All right. Hydrated salts. Hydrated salts are salts. Hydrated salt that have water of crystallization, that possess water crystallization or have water crystallization. Exactly. So that possess water of crystallization. Calculation, right? And they say what's the percentage?
There's one that used to give
Efflorescence. Don't worry. Today, I'll give you a trick. No, that one is different. That one's in chemical kinetics and chemical reactions. Should we do all those things together now? Now let me quickly teach you something in the rush. But just listen. And those ones, I'll tell you a story behind what I used to teach a student. So that's why I discovered that it's not me that teaches, it's the Holy Spirit that teaches. Because I taught the boy once, and I said, come forward. It was the next one. I said, so what is this now? And then, will this be efflorescent or deliquescent? He will make mistake again. The Holy Spirit just inspired me to give him Yoruba. This Yoruba I used to teach you, you will never ever forget again. See, as in if you marry, the one give birth, the proof that you went to school is this one. This one you will remember it. Eh? Let's continue. You will know. I said hydrated salt. Hydrated salt. I don't like the way you are sitting at the back. I like you in front.
Why is it that they are changing position?
Today.
To come and chat phone.
Okay. No, come. Leave your phone there to not be stolen, okay? Come forward. Come forward. Quickly. You to move forward. Come and sit here. I like her in front. Stay at the front, okay? What's that shape called? See, you look good in front. They possess of what? They possess what? Water of crystal. Water of. You know how to do that abbreviation? Water crystallization. It's called apocopy. What I call it? Ah, Jesus. Crystallization. Now, it means water crystallization simply means there's water in their salt. Exactly. There's water in their salt. Now, there are three groups of hydrated salt. We have the efflorescent salt. Their condition is called efflorescence. That is, they display what? Efflorescence. Then the second is deliquescent. Deliquescent salts. Their condition is deliquescence. Then we have hygroscopics. Hygroscopic salts. Hygroscopic salt. They display hygroscopy. Hygroscopy. We call them hygroscopics. Now, let me teach you, before I give you the definition, let me teach you what I said I taught that boy. So, after telling the definition, for like 1,502 times because I was counting it. Then I later resolved to saying this. Now, watch. Now, what is this? E, right? So, E, this thing means is from the Yoruba follow. From the Yoruba what?
Follow.
So, E follow. So, that is their salts that lose their water of crystallization when exposed to the atmosphere. So, E what?
Follow.
Exactly.
Yeah.
Then the liquid. What is this? D. In Yoruba it means what? Turn to, right? Liquid. So the liquid. So they are hydrated salts that will absorb water of crystallization from the atmosphere, and the water of crystallization will dissolve in them. So they turn to solution or liquid, anyhow you think of it. Is it clear? Then this one hygroscopic is the one that doesn't have the Yoruba. But once you remember this two, you know this one. This one also, when you expose it to the water of to the atmosphere, it will absorb water of crystallization, but it will not dissolve in it. It's not onto a solution. Do you understand now? Is it clear? So right, efflorescent salts are salts. Efflorescent salts are salts. Easy. They lose their water of crystallization. Efflorescent salts are salts that lose their water of crystallization. Crystallization on exposure to the atmosphere. They lose their water of crystallization on exposure to the atmosphere. Example is washing soda. No. Washing soda. What's the chemical formula? Na2CO3. Now, for example, if it had like 10H2O before, how do you even name this? Let me teach you how to name it. Sodium trioxocarbonate. 4. 10 is decahydrate. Is it clear? You already know this one normally. Then you now add decahydrate. If you expose this guy to the atmosphere, it might become Na2CO3 dot 2H2O. What has happened? It has lost 8 water of crystallization. So what would this now become? Trioxocarbonate 4 dihydrate. Is it clear? Alright. Now the next one. Also have another efflorescent substance. Vitriol, blue vitriol. CaSO4. That dot is to show you that it has water attached to it. But when you are looking for there are two salts in that one. One is K2SO4.Al2. In fact, you might not see dots in some places. Al2SO4. But before water, you put salt. Now look at this. 12H2. How do you name this guy? Potassium. Potassium tetrasulfate 6. Aluminium. 6. It's still 6. Then this dodecahydrate. Is it clear? If it's 11, undeca. Those things. Is it clear? Is it hard? The common question they ask about this, apart from this. Now, first listen also. You see these two guys are used as drying agents. Do you know why? It makes sense because they usually absorb water from something. Just now, okay. Put those down. This is blue vitriol. Have you put it down? Now let's write um, deliquescent salts. These are salts which absorb water crystallization from the atmosphere. These are salts which absorb water crystallization, which absorb water crystallization when exposed to the atmosphere. Water crystallization when exposed to the atmosphere. Water crystallization when exposed to the atmosphere. To the atmosphere. Then, so examples of deliquescent substances. We have deliquescent substances. We have
So like the deliquescent and the hygroscopic
drying agent, and because both of them are the one that usually absorb, but this one absorb and turn to liquid or solution, form a solution, but this one will absorb and will not form a solution. Is it correct? So example of the liquescent substances, how can I remember? For hygroscopic, we have silica gel, because those are drying agents, that's what I'm remembering. Silica gel, CaCl2. So this guy, sodium hydroxide. I know, sorry. Deliquescent salts. Which other salts do we use as drying agent? I think salts of sodium and, yeah, it makes sense because they form solution. So salts of potassium and salts of sodium, they are usually agro and deliquescent. Salts of ammonium, sodium and potassium, they are usually what? Deliquescent. Now, now, let's quickly talk about, before we deal with calculation, let's quickly talk about which salt is soluble in water and which salt is non-soluble in water. In our calculation class, we now do solubility and solubility curves. Hygroscopic. I said they absorb water visualization from the atmosphere, but do not form solution. Put it down that way. Example is silica gel, CaCl2, I think that is also a drying agent though. This guy, P4O10, is a very, H2SO4 is also a drying agent. Okay. Let me show you a table that I usually give to students. They absorb water absorption from the atmosphere, but they don't form solution. Alright, drying agents. You see, CaCl2, H2SO4, these are drying agents. The gases that are used to dry in the laboratory, we use them to dry gases. So the gases that they dry, this one can dry all acids except ammonia. Wait, I don't know why I'm forgetting this thing. You know that others be hold on. Wait. Among this one, all acids, all gases, rather. I'm sorry. All gases except ammonia. Which one again? Which other one? P4O10. I think it doesn't dry ammonia too. But this one is very, they don't use it often because of its, this one often because it's very strong. It's too strong, kind of. CaO is the only one that dries all gases, including, so this is one that they industrially use to dry ammonia gas. Now, I don't think it dries ammonia too, except ammonia. But CaO is the one that dries ammonia. Now, why does this one not dry ammonia? Because it will react with it to form ammonium chloride. But this one reacts with it to form a complex, usually in fact NaH4 plus, NH4SO4. So it doesn't react, it doesn't dry it. I don't know about this one, but this one is the only one that can dry it. It will not, it is inert to ammonia. Inert to ammonia means it doesn't react with ammonia. So you can use it to dry ammonia. Don't forget, quick line for drying ammonia. Is that clear? Alright. Now let's go to soluble and insoluble salts. Primer has written it. Soluble. There are a lot of things we are supposed to do about salt, but because we are pressed for time, because I'm supposed to teach you how to prepare salt. Yeah. Yeah. The insolubility of salt. Are you okay with that? What is wrong? You are scared. Don't be scared. Fear of what? Okay. Is it like your heart has been palpitating, beating fast? Big girl, scorpion killer. Sorry. You know, in those days when scorpion was everywhere, you know, we cleared a lot of them. One day, very big one, as big as the size of that room, came, wanted to attack. You see, it wasn't one. Nothing was with me. That was like John wanted to strike me. Like this. Do you understand? Then he came back, wanted to strike me again. I just went like. Then he just got to a time. His friend now came. The two of them, that one said, they colluded. Don't say if I want to strike him here, and you two attack him. You understand? So as down just came like this, I went like this. So I just saw the second one coming. 1, 2, 1, 2, 3, 4. Together. That was that. Alright, let's go. So everybody have salts. Now, how do you know salts that are soluble? See, use this mnemonic. Snap. Come on. Snack. Let's do snack. Snack. Now, sodium. No, let's use Let's just snap then. Do you know why we are using their names? I wanted us to use the symbols. So sodium, what will this be? Nitrate, actually. And this one, ammonium, not ammonia, and not aluminium. And some people think that A, they will think it is for that guy. Then this one, potassium. Any compound in which you see these guys will be soluble.
This is not.
Snack,
But now it's like
potassium now is potassium. So don't forget, any compound you see these guys, the what? Soluble. The what? Good. But so nitrate is NO3, NO3 minus. This one is sodium ion. This one ammonium ion. This guy K plus. We said all soluble. But you now see these guys. Please check on those other guys I talked about. I did not remember the deliquescent substance. But remind me on the group to send it. I didn't even prepare to teach you the acids and salt today. I was thinking I would just go to. It was physics that we stopped yesterday. What is it? So,
okay,
Daniel.
that's the point.
Okay. Why? Does he go somewhere today?
You don't say yesterday was the long.
No, okay. Okay. Now look at this one. I like to use copagma. 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 Now this stands for chlorides. Now listen, all chlorides are soluble except the chloride, all chlorides soluble. So anytime you see a chloride is soluble, but if it's chloride of P is for lead. Lead. Is that clear? Ag, silver, right? Then mercury. Now that of this guy to mercury. Hg. Now that of this guy too. Can you see it? The reflection? Okay. So that of there's also barium. Barium is also insoluble. Yes, I think so. I know. Barium is soluble. How many minutes in this thing? These guys, all chlorides, soluble. But if there's chlorides of this one, insoluble. But the remaining what? Soluble. Example now. Example, aluminium chloride. Aluminium chloride, soluble. Is it clear? Then the last one. The last one. This one has to do with sulfate. Snap, pragma. Sulfates are generally soluble. Sulfates, except except calcium, sulfate of calcium. I can't remember the mnemonic for this one. Mm. Suba cap. Suba cap. Is it cap? Yes. So all sulfates are soluble. All chlorides are soluble except this. How did I say you remember this one? Okay, plasma, right? But this one, supercap. All sulfates are soluble except calcium and except barium, calcium, and lead. Lead. Remember, potassium is always soluble. Is that clear? Don't forget this way. All sulfates are soluble. Well, but once it's barium sulfate, insoluble. So it was barium I wanted to remember. Barium is soluble. Barium chloride is soluble, but not barium sulfate. Don't forget. Snap, copagma, and subaca. Is that clear? Then also, this one, all of these ones are insoluble. All OH minus, insoluble. Except is OH minus of this. They are always soluble if it's for those.
Only those four.
So now I'll write a list of salts, a list of substances on the board now. If it's soluble, when something is soluble in water, what's the phase? What phase will it be in? Aqueous, God bless you. If it's not soluble, what phase will it remain? Solid. Is it clear? Alright. So just write in front S aqueous according to this rule. Should I rub the board off? Come, let me rub this board. Thank you. Don't worry. This breeze, it's been telling me something since I did not attend to it. That's why it's angry. Thank you. If it's soluble, right? Yes. Now the first one is okay. I should be writing their chemical formula already. Oh, I didn't tell you about carbonates too. Carbonates are generally insoluble too. Except those first three. Carbonates are, So let's do this stuff. Tell me if they are soluble, insoluble, soluble, and insoluble. Mm. Write it out now. Write it out. Alright, so now, is any NO3 aqueous or soluble or solid rather? Aqueous, because we said all sorts of sodium soluble, all sorts of nitrate soluble. So this guy also soluble, this guy also soluble, this guy soluble, this guy soluble. Any salt that has NAD, let's find them soluble. This guy soluble. Is it making sense? I'm first looking